All right, in this video, we are going to talk just a little bit about the beginning information you need to start Chapter 5. Chapter 5 starts to take a pivot where we will start to talk a little bit more about molecules, compounds. We're going to move away from that atomic model into how do those atoms hook together, create the molecules that create the 3D world that we live in. In this video, we're going to talk just a little bit about how to read chemical formulas and how to count the number of each atom and the total number of each atom in a chemical formula. Okay, let's get to it. Atoms don't really often exist on their own. They often combine to form molecules and compounds, and this drives a lot of chemical reactions, which we're going to talk about later in this unit. All the time, atoms are breaking apart, reconnecting, breaking apart, reconnecting, breaking apart, reconnecting to make new molecules time and time again. When atoms, again, are hooked together, we call that a molecule or a compound, as we talked way back in like Chapter 1, Chapter 2 time. But in this chapter, we're going to end up talking about 3 different types of compounds. So we're going to talk about ionic compounds, molecular compounds, and acids. As we start to talk about this, those aren't all the molecules we're going to talk about this semester. Those are just the few we're going to cover in this chapter for right now. As we move on and move forward, we're going to talk a little bit more about acids and bases. We'll talk about organic molecules and some more things like that. So there's more coming, but these are just the 3 basic ones we're going to talk about for right now. Molecule or compound, which word is right to use? I'm not too worried about splitting the difference between those 2 words. So the book, for some reason, is really concerned about this. However, if you're talking to a chemist, we'll use the word molecule and compound interchangeably, so don't worry about splitting the hair between that too much. If I'm really looking for some sort of response or you're worried about molecule or compound, you can always be sure to say that full name, like ionic compound, molecular compound, or acid. So I'm not just going to say is this a molecule or a compound? I would ask you is it an ionic compound? Is it a molecular compound? Or is it an acid, for example? Again, I'm going to use these interchangeably. All I'm meaning is some sort of individual grouping of atoms with a specific chemical formula. So if I'm saying molecule, that's what I mean. If I say compound, that's still also what I mean in the end. So again, if I want to mean specifically ionic compounds, I will say ionic compounds. If I want to mean molecular compound, I will say molecular compound. If I want to mean acid, I will say acid in that case. So just kind of wanted to clear up that little bit that I thought was a little superfluous in the book from the beginning. So molecules and compounds, that's the direction we're headed, but we're not splitting the hairs there on that definitional difference. If we're going to be talking about molecules, first things first, we have to understand and read chemical formulas. So chemical formulas are a shorthand way to represent a chemical molecule. So it's used to really indicate the composition of the compound. So down here on the bottom of the screen, you can see that we have H2O. So H2O here, we know that as water, right? We kind of talked about that a little bit this semester. 2 hydrogen atoms, 1 oxygen atom, boom, we've got water. So this chemical formula tells us about that composition of water. And what it does is it displays the ratio of each type of atom contained within a compound. So here I see that I have hydrogen and I have this little subscript 2 afterwards. So this chemical formula uses that chemical symbol from the periodic table. Then it has that 2 after it, and that little subscript 2 tells us that we have 2 hydrogen atoms. So those subscripts always just apply to the thing that's directly in front of it. So that 2 does not apply to the oxygen, and it wouldn't apply to anything else over here in front. Whatever that subscript applies to is just to what's directly in front of it. here, again, this chemical formula is telling us that we have 2 hydrogen atoms. And then if we look over here, we see that that oxygen does not have anything written after it. It doesn't have one of those little number subscripts. So what do we do with that oxygen? Well, what's happening here is that we have an implied subscript of 1. So if an atom is like not in the chemical formula at all, like iron, right? If iron was in this complex, we would see Fe written in the chemical formula. But it's not in that chemical, it's not in this compound that is water, so it's not written in there. So if something is written into the chemical formula, that means there must be at least 1 atom of that kind in that chemical formula. So if we don't see a subscript, we can just go ahead and boom, we can assume that subscript is 1. So it's kind of like an imaginary number 1 down here. Remember our theme of the semester, chemists are lazy, right? We don't want to have to write everything out. So if I'm writing it into the chemical formula, obviously you have at least 1 of that thing. So you can assume that that number is 1 without me explicitly writing it down. Okay, so that's kind of how you can read a chemical formula. Again, that subscript, that little number down here, always applies just to the number in front of it. And if you do not see a subscript, there's 1 of that atom. So what I hope that you're able to do by the end of these slides is to be able to look at a chemical formula, and we're going to be able to count the number of atoms in it. So I'm going to teach you how to count the number of each type of individual atom, and we'll also count the total number of atoms in a molecule or in a chemical formula as well. So a quick warning, we're going to have a couple warnings throughout Chapter 5. I want to warn you to always triple check that you're using the correct chemical symbol. So I'm always going to give you the periodic table as a reference. I'm always going to let you go back and forth between the name and that chemical symbol. So you'll always have that periodic table to triple check, reference, go back to, okay? So if you want to talk about selenium, you're going to use capital S, lowercase e. You want to use silicon, you're going to use capital S, lowercase I. You're going to talk about sulfur, it's just that capital S, okay? So don't get them confused. Don't just guess and hope you're right. You'll always have that reference tool there for you. And one of the most important things I think you can do this semester in an introductory chemistry class is to learn how to use the periodic table. So please use it as your reference, use it as a tool. It's there for your guidance. I want to say this as well, just to make it explicitly clear. If you use the wrong chemical symbol, I may count your answer wrong because I'm not sure what you're talking about, or you're talking about the wrong compound, okay? So maybe you get a little mixed up and you write capital S, lowercase l for silicon for some reason. I'm not going to know what you're talking about, so there's a chance that your answer is going to be counted wrong. So that's why it's so important that you can use the periodic table to go back and forth between these things so that you know exactly what you're talking about and you can tell me exactly what you're talking about in the end, or whoever is reading your work in the future too, right? So the other huge forewarning I have about chemical formulas is this. They must be properly formatted, okay? So remember how I showed you on this slide that hydrogen has a subscript 2 here? You can see that 2 very clearly hangs below the line where you would kind of write the bottom of the H and the O. So when we're talking about chemical formulas, you have got to be absolutely certain you're writing that little number 2 so that it hangs below that line there, where kind of a line on your paper would imagine, like if you put your imagination to it, where that line on the paper would be in the end. So make sure you're absolutely writing your chemical formulas that way. So, you know, there's a chance in Canvas that I might give you a pass and say, you don't need to type it into Canvas with that subscript, because it can be quite tricky in Canvas to type those things in, and it doesn't necessarily always give you that option based upon the kind of text box it presents you with. So if I find it to be a time where it's appropriate to just write them as normal sized numbers, I will put in that question specifically, you do not need to type the number as a subscript. okay? And that is the only free pass you get, and that just has to do with the mystic, magic, wonderfulness of how Canvas works. So again, I will explicitly say in the question, you do not need to use subscripts if you can get by without them. Otherwise, I expect you to actually format that properly as subscripts, especially when you're writing by hand, okay? So when you are writing by hand, I absolutely expect that you will be able to, write that down properly. It's not like a trick in the computer to figure out, not something you haven't experienced before. So if you're going to write things by hand in lab or on an assignment and turn it in, make sure you're using those subscripts. It's really hard for me to tell what's going on if I'm not expecting that. And to be honest, it's technically wrong. Even though you might have the right numbers, you might have everything in the right place. Chemical formulas are denoted this way so that when I look at it, I know it's a chemical formula. So if you don't use those subscripts, it's not going to look like a chemical formula to your reader or whoever is coming back to check out what you wrote down. So kind of keep that in mind as we move forward here. Those are kind of my expectations for when you write a chemical formula. So let's talk just a little bit here about the law of constant composition. So even though molecules are always breaking apart and creating new molecules, everything kind of shifts and moves in the universe. We know that we have a certain compound because compounds always have the same type and number of each atom. So the ratio of each element will be the same in each sample of the same compound. So it doesn't matter if it's the water in my water bottle, it doesn't matter if it's the water in the bathroom or in the water fountains or what have you, or in the river, in Lake Michigan, in the oceans, wherever you're going to find water on Mars. On Mars? Water? So wherever you're going to find samples of water, it's going to consist of 2 hydrogens and 1 oxygen, right? So no matter what water I'm looking at, if it's water, it's 2 hydrogens, 1 oxygen, H2O, okay? So the ratio of each element is the same in each sample of the same compound, no matter where it comes from. So in the end, this kind of reminds me of how we define elements by their number of protons. We define compounds by their ratio and type of atoms within that compound, okay? So elements and compounds have very different behaviors depending upon how they exist in these molecules. And different ratios of different elements have different properties as well. So H2O is water, H2O2 is hydrogen peroxide, right? And let's say I'm outside and I'm working on building a fence and I cut my arm and I got some dirt in it, right? In that cut. If I pour water onto that cut, what's going to happen is it's just going to kind of wash the dirt and it's going to get it clean, but it's not really doing more than kind of washing, just kind of rinsing generally, right? But if I pour that hydrogen peroxide on my cut, if you've never done this before, you should try this sometime. What happens is it's actually kind of doing a bit of sterilization in that cut. So what's happening is you'll start to see it bubble up. You'll see kind of that chemical reaction happen. It stings a little bit, so be careful. But it's going to sterilize a little bit. So these 2 compounds have very different properties. And again, you may have experienced them before, right? H2O, water, and H2O2, hydrogen peroxide. Those chemical formulas are very, very similar, but they have very different behaviors, right? So there's like a very classic joke in chemistry, right? 2 guys walk into a bar. The first one says, hey, I'll have an H2O. The second one says, I'll have an H2O2. Second guy dies, right? Because he ordered a hydrogen peroxide. First guy ordered a water. So that's kind of the deal here, is they have very different properties, very different behaviors. You're not going to want to be drinking hydrogen peroxide. So you have to understand that those ratios of those elements give them very different behaviors. So that's kind of why we define compounds this way, is because we can't just know the type of atom and kind of hedge our bets that way. We also have to know how many of each type of atom, those ratios of each type of atom, so that we can better understand their molecular structure and their end game behavior then too. All right, so let's go ahead and do some examples for how we can count the number of atoms in a chemical formula. So the first formula you see on your screen is CO2. So first and foremost, we're going to talk about CO2 here. So let's figure out how many carbon atoms are in this compound. So again, our chemical formula is CO2. So if I look at that chemical formula, what I see is that I do not have any numbers after carbon. So it's almost like there's a little imaginary 1 sitting there after the carbon. Again, we wouldn't put it if it wasn't important. So that tells me if there's no subscript, I have 1 carbon, okay, 1 carbon. And then I look to my oxygen. I see here that I have the number 2 after oxygen. So if I see that subscript 2, again, that subscript only applies to oxygen. It has nothing to do with the carbon, okay? So this tells me that I have 2 oxygen atoms, okay? 2 oxygen atoms. And then if I want to know the total number of atoms, I can say, okay, I have 1 carbon atom, I have 2 oxygen atoms, so I must have 3 total atoms in that chemical formula. So in the end, the chemical formula CO2, which is carbon dioxide, right? Breathe in, breathing out that carbon dioxide. That carbon dioxide has 1 carbon and 2 oxygens in the end. So I am going to leave you to work on C6H12O6, that's sugar, and C4H10, which is butane. So there's some answers in the slides about this as well. So you can find all of the answers here. It would be some good practice to do on your own to make sure that you're able to count those numbers of atoms in a chemical formula. And if you have any trouble with this, please inbox me on Canvas. We can talk through your questions, or if you want to stop in office hours, that's a great time as well to ask questions about this kind of stuff. And this is going to be extremely important as we start to move forward. Now that we're talking about molecules, we'll end up talking about chemical reactions. So if you're not prepared to be able to count the number of atoms present in a chemical formula, it's going to really, really stink when you get to chemical reactions because you're going to have to relearn this skill all over again. So make sure you know what a chemical formula represents, that each individual compound has a very separate chemical formula representing the number and type of atoms within that formula, and that you know how to count the number of atoms as well as the total number of atoms in a chemical formula. So after you've watched this video, go check out some of the compounds like ionic compounds, molecular compounds, and acids. And then at the end, we'll talk just a little bit more in kind of a final part about some more generic things that we can learn from chemical formulas as well. So I'll see you in the next